All right. Hello again, and here we are entering the lesson on work and energy, and it will be lesson number 7. So let us begin. We will discuss work, kinetic energy, potential energy, both gravitational and elastic, work energy theorem, mechanical energy, conservation of energy, and power. All right, let's start with work. Remember that work is the process of transferring energy in or out of a system or a thing, an object, if it's a single thing. Remember that work is only done by the parallel component or anti-parallel component, um, parallel to the direction of motion or anti-parallel, meaning the opposite direction. So in the common case where we see these images like this and we say there's a force F being applied, this piece is Fx, right? This is the angle that the force is being applied at. Fx is F cos theta, right? F, just F representing the magnitude, of course. This is magnitude here. And these are both vectors, right? So you have to remember that this theta in cos theta is in reference to the angle between the force vector and the displacement vector, because that's what delta x is. That's your displacement vector, right? So if you move from one spot to another spot, usually we call that the displacement, like this. And then we're looking for components that are either parallel to that, like Fx, which does positive work as it moves from one spot to the other spot on the right, or forces that are not, like anti-parallel, which friction for sure would be anti-parallel, 180 degrees, right? In that case, again, the angle is between the delta x vector and whatever the force is that you're interested in figuring out what work is being done by that force. So for this case, or for the friction case, it would be delta x, the angle between delta x and an opposite direction vector is 180 degrees. Cos of 180 is actually -1, and it just takes care of referencing the idea that work is negative as frictional forces act on something as it moves in any direction. Um, okay, so there's that part. Let's comment quickly on kinetic energy. Kinetic energy is proportional to the mass, and it's proportional to v squared. I think that's the most important one, but I guess they're both relevant. So twice as much speed quadruples your kinetic energy, twice as much mass, assuming you're moving at the same speed. When you're comparing two things, if one has twice as much mass, then we have twice as much kinetic energy because they're directly proportional. Our potential energy formula is mgh, right? I'd say most importantly, recognizing that your potential energy is proportional to h. So 2 times higher is twice as much potential energy, 3 times higher is 3 times as much potential energy, and so on and so forth. Right? Potential energy versus h graph should be linear for that reason. They're proportional to each other, right? What would the slope be? Slope would be mg, because this is now y, this is now h is on our x-axis, so that means the slope m would be mg, right? Kinetic energy versus, let's say, velocity graph, if they happen to give it, would have to be curved. Why? Because there's a square. There's a square in the formula. K is proportional to v squared. If they did a k versus m, which they never do, it would be linear because they're proportional, right? Okay. You also have the elastic potential energy that we have to think about, right? When we have a spring that's like this, and then we come over and we compress it, or um, we stretch it out to here. In both cases, the elongation in this first case on the right, or the compression um, on the left, those both will store energy, elastic potential energy. And that elastic potential energy again is represented as U for potential energy, S for elastic spring energy. That's why we use the S for spring. 1/2 k delta x squared. Right. Note, most worthy note, in my opinion at least, is not k. Okay. The most worthy note is that the potential energy in the spring is proportional to the distance you stretch or compress it squared. So it means if you compress it twice as much, you actually store 2 squared 4 times as much energy. Or if you stretch it and then stretch it twice as far, you now again store 2 squared 4 times as much energy. Or if you did it 3 times further in either direction, 3 squares 9 times as much energy stored, which is why, again, a graph would have to look curved because of that quick increase in potential energy for each little distance you compress or stretch. Yeah. Technically, I will point out if this is the graph here, then the slope at some distance delta x, now we'd have to be talking tangent line slope, that would have to be k delta x at that position. What is k delta x? That is the spring force, right? Because you should know that for any potential energy versus I shouldn't say that. I should say for any energy graph, any energy versus distance graph, which we're looking at here in the bottom right, this is always a force, like we did on the last screen for U equals mgh, right? The slope here was mg, which is a force. It's the gravity force. In this other case that I'm showing on the far right, it's not a constant force because as you stretch it further and further, delta x increases. Build elastic potential for it increases. That's why this tangent slope here that I've drawn on the right would actually increase, right? Be enough much steeper one at that point, and that point would be referencing a further delta x, right? And that further delta x means the tangent slope at that point right there would have to be steeper. What would the slope that be representative of? K delta x, the spring force at that position. Okay. Moving on. We can look at, I guess, projectile motion very quickly. Something's being launched. Typical image like this. Remember that the initial kinetic energy of a launch would be your normal 1/2 mv squared, where v would represent the launch speed, right? Whatever speed it has at launch. Usually they do some, often reference this top speed up here. Remember, this is just Vx. So you have to remember that Vx is set at launch, which is the initial speed cos theta, since that's an adjacent component. So technically Vx up at the top, again, is the same value because it's a constant horizontal speed as it goes along. These are equal distances per second. We've talked about that, right? So if someone said the kinetic energy at the top, we would have 1/2 mv at the top squared. Well, this is v at the top, right? So we'd end up with 1/2 m, and then we have v cos theta squared, right? Because this is Vx at the top. That would be mindful that there's, you could re-express that 1/2 m v squared cos theta squared. Just be mindful of it. I'm not expecting that you would memorize this resulting form. Just be mindful. At the top, the kinetic energy relates just to the horizontal speed. The most common mistake is that, again, that it's just the full speed that it had at launch. It still has that at the top. It doesn't. There's a loss of energy from comparing the initial launch to the top because potential energy has increased, right? So some of that launch energy, this amount over here on the left, some of this launch energy, kinetic energy, transforms and converts, right, to potential energy at the top. So you can't have the same kinetic energy at the launch and at the top. It has to be less kinetic energy at the top. Why less? Because that difference turned into potential energy, which is why we would certainly, model that idea. They had you compare these 2 points again. This is K initial, and then here we have a potential energy final plus a kinetic energy final in terms of the total mechanical energy. At the bottom, the total mechanical energy is just kinetic. And conservation of energy, I guess I'm mentioning it there for the first time, would suggest that the kinetic energy, short of any loss of energy due to air resistance, which we're assuming is true, there's certainly plenty of scenarios where that loss of energy could be pretty small, never zero, since it's in a vacuum, would equal K final plus the potential energy final. I mean, could you technically have to express K and U? Yeah, you certainly could, and solve or create a formula for one of those variables like h, or yeah, you could, but I mean, I can't go through all those, right? But just know that this is the general idea of how it's modeled. And lastly, know that at landing, which is the other most common thing that they reference, that final kinetic energy it has, boom, when it hits the ground, is equal to the initial kinetic energy, which means that the final speed in magnitude is equal to the initial speed in magnitude. So whatever energy, again, we're assuming that you haven't lost energy throughout the trajectory. So whatever energy you leave the ground with, you must return to the ground with the same energy. That's the conservation of energy. At the ground level, there's no potential. So all energy forms must be in the form of kinetic, right? Of course, if it hits the ground, which things do, it makes a sound. That energy is dissipated as sound. That energy is dissipated as heat if the thing vibrates after it hits. Um, that kind of stuff. That's true. I mean, that energy has to get dissipated somehow. Maybe it dents the lawn or something like that. And well, if it dents the lawn, then that's work, right? Force times distance. The distance would be the distance depth of the dent, the force to actually push the soil down. That's where it all goes. That's where it all goes. Now looking over, I'm just kind of going along with my little chart here that I made to make sure I try to thoroughly do it. Thoroughly do this review. Remember, we were Atwood machine. You should know that as this one goes down and this heavy, lighter one goes up, this is the big heavy one, that the potential energy of the system after heat ends up down here, right? So in the next image, he's all the way down on the ground, the big guy, and this guy is dangling up here, right? So the potential energy of the system is going to be going down for the system. And that can be confusing again because you have one going down and one going up. And then, well, how do I figure out that? I'm just telling you that for all Atwood machines like this one, the total potential energy of the system has to have gone down because it produced kinetic energy. The result of releasing it, they all of a sudden start moving and getting kinetic energy. Where is that energy coming from? It must be coming from being transformed from potential energy of the mass pulley Earth system. And you remember how I feel about that, but don't forget about it. About the mass pulley Earth system. That potential energy is just turning into kinetic energy. No different than just dropping a basketball, right? As you drop it and it falls, the potential energy goes down, kinetic energy goes up. That's also what's happening here. It's a little more confusing because you have one going down, one going up, but just know the general idea is true. Kinetic energy is going up, potential energy must be going down. And also the center of mass ends up, the center of mass was originally up here, and the center of mass is eventually at a lower point. So the center of mass actually moves down for the system. That's the center of mass of the system. What happens to the total mechanical energy? Short of any loss of air, force of energy due to forces like air resistance, total mechanical energy is always constant, right? As this thing evolves. In the real world, no, it's not true, right? There's always maybe some friction along the axle and the pulley. There's some air resistance, and some of that energy gets given out, is lost from the system. And so the kinetic energies they finally have at the end is not equal to the original potential energy. There's a difference there. And that loss, that difference, that is the loss from whatever mechanisms might have been stealing some of that energy, air resistance and friction along the axle of the pulley. Moving on. We're going to talk about a ramp and work. Sometimes we see this problem where somebody, show a person and they're applying a force and it goes up the ramp. And you have to know that the work, again, is generally F cos theta, as we said, times delta x. That's just a stamp kind of formula. If they say that it's going up the ramp at a constant speed, which a lot of times they do, not sure why they like that so much, maybe it's because it's a little easier, then we know that the upward force, and this is no friction, which would make it hard to push it up this. If there's no friction to actually be able to have some traction. So if it's a person, then now obviously impossible. I think they still show people walking up no friction ramps. That ain't possible. Don't worry about that. This is the mg theta amount of gravity's x component, right? And if it's going at a constant speed, then there's no acceleration, and that means the net force is zero, right? If the net force is zero, then the forces must be balanced, even while moving, right? Working on that means that that's used to move distance speed around. is a gravity component. It might be worth explain that. Think about it. My I lost my screen. Shoot, what just happened? Oh boy. Yeah, good. Bear with me. I wish there was a pause button on this Google Meet stuff, but there is not. Um, my best to see if I can pull it back up again. Did it just close out all on its own? Did I even lose that? No, it's still there. Oh, there it is. Okay. So back here. That size. So it depends on, I guess how you express this depends on what they're looking for. Just be aware that what I have here is true. It would just be mg sine theta would be the force, right? So that would be the amount of force. So I should just put, because that might confuse you. I don't want to confuse you too much. So I have to be careful not to confuse you. So just know that it's the force that you're using to apply in the upward direction, right? Times d times cos theta, where d is now the distance, along the ramp at d. And we would usually reference this as mg. Mg, in fact, d cos theta. Yeah, that's what's okay. So just take away the cos theta. Let's just think of work as a force times a distance. And that would probably be more helpful. If that's true, because that's the cosine and the sine can't contradict each other. So if we're thinking of work as just a force times a distance, then the force that we're using is to move up the ramp at a constant speed is mg sine theta, right? That's what we talked about, times d, right? And so when we look at the d sine theta part, the triangle, this is d theta. This is d sine theta, right? Over here on the right, that's d sine theta on the right. That's the height. D sine theta. That's h, right? So d sine theta is just h, right? So that's an important awareness. That the work done by moving it up the ramp like this is still just equal to the potential energy that you have increased the system, the amount of potential energy it's gained. Because the amount of potential energy that it gains is going from here to here. It's just dependent on that, right? If you were to lift it just straight up with a pulley from here to here, what would the amount of work be? Mg, if you were lifting it at a constant force. I meant if you were lifting it with a constant speed, then the force you were using to lift it at a constant speed, if it was straight up with a rope, would be still mg. And then the distance would be h, right? So it's still mgh, amount of work to lift it with a pulley straight up. Mgh amount of work still to push it up the ramp. So why do people use ramps? Because the amount of force is mg sine theta, which is a fraction of the weight. So there's less, force requirement to push something up a ramp. It's easier to push something up a ramp than to lift it straight up. When you lift it straight up, you got to apply a force fully equal to its weight, which you might not be able to do if it's a piano or something, right? But if you can push it up a ramp, now the force you apply in the direction up the ramp is mg sine theta, which is a fraction of its weight. That's the reason, right? That's why it's called a machine, but we've been talking about machine. But it is a machine. A ramp is a wedge, essentially. There's a mechanical advantage there, which allows you to move something with less force. But the trade-off is you have to go larger distance. That's why the distance along the ramp is longer than if you go just straight up from here to here. Then you're going to use more force, but there's going to be shorter distance. Okay, I think I covered that part. Be aware that they could do the opposite. They could go like this and say, oh, block, just no friction again, and they put a block on a ramp and it flies down the ramp. It flies down the ramp, and they say, what is the amount of work done by gravity? Well, again, that work involves the force in the direction of movement. The force in the direction of movement is mg sine theta. And just be aware of what I'm saying here, that if you were to write FD cos theta as the general stamp formula, and then you got other things like sine, like I have here, that's actually wrong. It's the easiest way, once you're doing trig stuff with work, easiest way to deal with it is the work is just do force times distance, then look at your picture, figure out what the force is in the direction of its movement, which in this case was mg sine theta, and multiply that times d. But do we get the same result? Is d sine theta still h? Mgh. Yep. Is it positive work? Yeah. Yeah, gravity is going to speed you up. Positive work will increase your kinetic energy, right? And what will the amount of energy it be that gravity gives to this block as it slid down the ramp? Mgh. How much did it start? How much mechanical energy did it start with at the top? Mgh. How much do you get out of it? Mgh. It'll only give you what you put in, right? What do you mean what you put in? Well, how did it get to that point? Well, then that block had to start somewhere here, and somebody had to do work. Positive work. In what amount? Mgh amount. Might be 100 joules to get it up there. Then you let it slide down, and that mechanical energy of 100 joules now turns into kinetic energy at the bottom. How much work has actually occurred from gravity as it slides down? 100 joules. It turns into kinetic energy, right? Which brings us to the work kinetic energy theorem. The net work is equal to the change in kinetic energy, right? Be aware that when we say that we're talking net work, it's just the sum of however many things apply a force. That was a box, a simple example of a box just moving across the floor. You need to know that the gravity force and the normal force do zero work based on the idea that there has to be a component in the direction of its movement in order for that force to transfer energy to it to do work. And for Fn, there's no component to the right, it's straight up. And for Fg, there's no component to the right if it's moving to the right, it's straight down, right? That's the whole, when we again look at F equals, I didn't mean to say F twice, work equals F cos theta, whatever the force might be there, again, it's just a state. This was Fn, right? To right times d. If this was Fn, then theta represents the angle between Fn and d. D is to the right, displacement vector. Fn is straight up. The angle between those are 90 degrees, and cosine 90 is 0. So know that the work done by any force that's perpendicular to the direction it's moving is 0. So no work done by normal force, no work done by gravity. The applied force could do some work, and be aware that the frictional force could do some work because there's a component that's in that direction. And I lost it again. I'm sorry that my device is not performing as well as I would like it right now. Let's try again, see if we can get it back on. Okay, sorry about that. So know that, like in this problem that we're looking at, this would be like Fn plus the work. This would be like the work done by normal force plus the work done by the keep writing F's, plus the work done by the gravity force plus the work done by the applied force. Plus the work done by the applied force plus the work done by friction. This one would be negative, right? The frictional force work is negative, right? These are 0, right? Because of the reasons I just described, they're perpendicular to the direction of its movement. This one would be positive, right? Remember, there's positive and negative work. And back on our diagram on the bottom left, there's your friction force, right? So that's a component of the forces in the opposite direction of movement. It's going to do negative work, right? And when you're trying to model that amount of work done by friction, the force of friction, magnitude times d. I mean, you could put again cos theta if you really wanted to there, but again, the direction of movement might be this way. The force of friction is this way. We would say that the angle between those is 180 degrees. And when we put in 180 and do cos of 180, it's just -1. So it's just trying to help us out and tell us that the work done by friction is going to be negative. I don't usually bother with it. I just know in my head that if I'm looking at frictional force work, it's going to be negative. And then we do our normal, mu k. This has to be sliding friction, right? Mg d, because again, it's usually mu k times normal force, and we've already been there, done all that, right? The normal force is equal to mg, and so you take out Fn, you put mg, right? So this is an expression with a negative in front of it. You definitely want to have a negative in front of it for the work done by friction. So if they were, some positive work in the forward direction. It would be that force in the forward direction times the distance it moved. That would come out as some positive number. They say, what is the change in kinetic energy of the object as it moves from one point to the other point, including friction? Then again, you'd have to figure out how much work was done by the positive force, that force component in that direction, in the forward direction, times the distance. Maybe it came out as 100 joules. And then when you work out this one, it might come out as negative 30 joules. And that means 30 joules has been lost. 30 joules of kinetic energy has been dissipated as heat underneath the block while you slid it to the environment. So what's the net work? 100 minus 30, 70 joules. So what is the change in kinetic energy of the object? 70 joules, if that were the numbers. I'm just saying that to illustrate the idea, right? Remember, delta anything is final minus initial. It's always the final value minus the initial value, right? So delta K is always final minus initial. So if we're doing that, the net work, again, is equal to delta K. And in a lot of problems, it starts with no motion, and the initial kinetic energy is 0. Then once you've worked out the net work, based on what I just described up here, then that net work gets set equal to 1/2 mv squared. And they might ask, based on this information about work, forces, and distances, what is the final speed of the block? And you could technically solve for that. I mean, technically, you could use Newton's laws and say, I'm not going to talk about energy at all. But be careful there, because if it's a free response question and they're prompting you to use work and energy things, don't go, a different direction, because you might not you could get the right answer. They might say you didn't demonstrate an understanding of what we were prompting you to do, right? Because giving me information about forces and distances, I don't need to know anything about work and energy. If you're asking what the final speed is after moving 5 meters, I can do Newton's second law. I can figure out what the net force is. I could work out the acceleration, A equals F net over M. And I could use V final squared equals V initial squared plus 2AD. Give me the D. I know A from Newton's second law. And I could find V final, which is squared in that equation. Don't do it, though. If they're prompting you for this stuff, this is what you have to do. Moving on. Remember that we have work is expressed as a area, right? So if they show you a force versus distance graph, then these geometrical distances, or I meant to say these geometrical shapes, as it moves from one spot to another spot, D is the distance it's moved, right? These represent the work or kinetic energy. It's important for you to recognize that, right? If this square here, whatever the surface area of it is, you have to do, again, height times width. If it comes out as 50 joules and they asked, what is the work done up to this position right here? 50 joules, that's the first square. All right, 50 joules. What's the change in kinetic energy then? 50 joules. That's the work kinetic energy theorem. So you can't lose track of that connection. But those areas don't just represent don't just represent work. They also represent change in kinetic energy, because work is equal to the change in kinetic energy. That's the work energy theorem, right? Also a reminder that those can be negative, as all can be the case for all of the graphs that you guys do. You can have it go like this. That means this would be a positive work or a positive change in kinetic energy. This one would be negative work or a negative change in kinetic energy, meaning you're losing kinetic energy, because in that little segment it's representing a force that's technically a negative force. That assumes that you're still moving forward, but feeling a negative force, and so that's causing you to slow down. We did that with the robot earlier in the year on my screen. Remember that particular lesson? It's challenging to think about. And then this one over here again, this would also be representative of some amount of work, negative, in this case, negative work or negative change in kinetic energy. And if they asked what is the net work, it's the area of this one minus the area of this one minus the area of this one. You have to be aware that those areas underneath the x-axis represent negative something. In this case, it's negative work. If it was the kinetic energy stuff, the kinematic stuff, and we were looking at a versus t graph, this was an A versus T graph, those areas underneath that would represent a negative delta V, and the one that's on the top left would be a positive delta V, right? But they're going to ask what's the net. You got to figure out what the geometry shapes are, work out their triangle areas, the square areas. Remember, there's to assign pluses to the ones above the x-axis, minuses to the ones below the x-axis, add them up. They might ask you to then to, use that number and stick it into right into there. Make sure you recognize that that area, result total area, goes right into that. And that means if that becomes a number, you could technically solve for some speed that it has, at this distance over here, which they might show on the graph as, 10 meters after it's been pushed 10 meters. That would be V now. This here would be solving for V after it's been pushed 10 meters. Okay, moving on. Now we're going to look at also pointing out that any energy versus position graph, energy versus position graph represent, let's just do one like this. I just want to point out that the slope is equal to the force used to change. It's really the net, I should say, the net force used to change the energy of whatever it is. So just know that the slope of in general, just the slope of an energy versus position graph is force. I'll give you an example. Potential energy is a form of energy versus H. And the idea that, what if we graphed mgh for something that was just being lifted higher and higher and higher? Right? And now we know that H is on the x-axis, U is on the y-axis, which tells us the slope, since this is a linear graph. The slope is mg. Is that a force? Yeah, that's the weight of the object, Fg. Right? So in this case, the slope equals the weight. What about if we looked at another example where they were giving us, so I'll actually come back to the other example. Now we're going to talk about the springs. So you start off with a spring, right, like this, and then you either compress it like this, or you stretch it out like this. And these are the distances that you either stretched it or compressed it. These would be delta x distances of compression or stretched distances. Remember, the spring elastic potential energy is 1/2 k delta x squared, right? 1/2 k delta x squared, which I think I might have mentioned before. So I wanted you to know, like, how would that play out on a graph? Because that's sometimes they ask, graph out the potential energy stored in a spring as it's stretched. Well, based on that formula, 1/2 k delta x squared, and it must be parabolic, right? Another important point is then now that means the tangent slope, the slope of this at some distance, maybe delta x is 3 centimeters, let's say. What does the slope of that tangent line represent? Well, we said force. Any position versus distance graph, the slope has to be force. So what force are we talking? It's k delta x. What is that? That's the spring force at a position of x delta x equals 3. Right? If we did it at x equals 4 or x equals 5 centimeters, then that slope would have been steeper. That would make sense. More steepness means more spring force. Oh yeah, you stretched it further. It's going to be more. Okay. Moving on to the next one. For that, I'm going to have to. Yeah, I think that's maybe what I will do. Well, I'll just see what happens. Not very happy with iPad. It's really not my iPad's fault. It's my internet's issue. All right, back again. Keeps dropping connection. So sometimes they do this sort of thing. The spring is originally shown like this, and then somebody compresses it like this, and they're going to shoot it off, right? So you need to know that the total potential energy in this case is 1/2 k delta x squared, where this right here, this distance is delta x, right? And that means when it's launched, when that thing comes flying off the edge, how much kinetic energy will it have at that point? However much potential energy was stored in the spring. It's a full transformation of energy, short of any loss of energy due to heat or friction, which is what they'll say. Then this kinetic energy would be equal to 1/2 k delta x squared, right? 1/2 mv squared, and this now represents the initial speed when it comes off of the edge. Vi represents now the initial velocity, edge velocity, right? Which that could turn right into one of those projectile motion problems, right? So let me point out that if you were to solve that for v, which is often what you have to do, the 1/2 gets canceled out. Divide m to the other side. I end up with v initial squared equals k over m times delta x squared. And then when I square root this one and I square root this one, that's actually omega, interestingly, right? If it was glued to the spring, then it would oscillate back and forth with a angular frequency of square root of k over m. But usually if it's just being launched off, we just leave it like that. Square root of k over m, and then the delta x, because it's delta x square root of delta x squared. So this would be the launch speed. Worthy of noting that that launch speed is proportional to delta x. So if you were to double the compression up on the table there, push it in twice as far before you release it, and then let it go, it should come off the edge of the table with twice as much speed because of that right there, right? What else is there to say? Then there's the other one where, there's a spring that's naturally at rest like this, and then we jam it down, and we stick a ball onto it, and it comes up here, right? And you need to know that that's another scenario where the potential spring energy is now converting. If you're looking at just at the endpoints, yeah, in between it converts to kinetic energy, but at the two endpoints, it's just turning into gravitational potential energy. So it's just a conversion of spring energy that's stored in the spring to gravitational energy storage. And short of any loss of energy, those would be equal, right? So US initial would be equal to UG final. 1/2 K delta X squared equals MGH final. And could you technically, have to solve for maybe H final? Yeah. Give you all the other things. How high does it go? I'll plug it in, solve for H, derive a formula if you have to. More often than not, they actually do this and ask you to find out what K is. They tell you what the final height is that it goes to. They give you the mass of the ball. They give you the spring constant for the K. And then I'm sorry, I didn't say that. They give you the compression distance, delta X, the mass, and how high it goes. The only unknown actually being K. That comes through in experimental problems for FRQs. And then you have to use that information to try to figure out what the spring constant is based on how high it went. Total mechanical energy, again, for this scenario remains constant, right? It's always almost, not always, but as long as you're looking at a system, like in this case, it's the ball spring earth system, then any energy transformations that occur within that system won't change the overall mechanical energy of the system. It will change just what type they are inside of that system, but not actually change the overall mechanical energy. Good. I'm done with that page. Hopefully just another little bit here. Know that for this particular problem, when this is frictional like this, if something's being dragged across the surface like this, and they say it's moving at a constant speed, that the network would be zero. You have to be aware that if they describe something that is moving at a constant speed along a flat surface, that means its potential energy isn't increasing. Its kinetic energy isn't increasing because you just said it's going at a constant speed. That means delta K, in this case would be zero. And based on the kinetic energy theorem, if delta K is zero, then the network must be zero. That means although you are doing positive work on this side, that same amount of energy is leaking out as negative work as heat simultaneously. It's like adding water to a pool that also has a hole in it on the bottom. And the water level doesn't change. For every little bit of water you put in, it leaks out the bottom simultaneously, and the water level doesn't change. So be aware of that. Also be aware if they happen to ask you to model that, then the forward force times the forward force that you're pulling in the forward direction is equal to the backwards force, right? So sometimes just that alone, they ask, okay, based on that, what's the coefficient of kinetic friction? All right. Lastly, be aware that there's no work again done by these forces, right? I don't think I said that yet. If this thing was moving like this, Remember that when we say F cos theta, F, cos theta times D, that if the again, that theta is the angle between the displacement vector and the force vector. So if that's 90 degrees, then that's zero. So that, because it has to be a direction, a force component in the direction of motion or against the direction of motion. So this guy, zero work. This guy, zero work. Moving on. Now let's talk about planets real quick. You got planet 1 and planet 2. They're some distance apart. Technically, that distance goes center to center, like this. They're feeling equal force. You should know that regardless of how big or small each one is. It's Newton's third law. Don't fall for that question. Oop, don't know what just happened, but it looks like I just deleted what I had. Center to center. They feel equal amounts of force. The potential energy of the system is actually this 1m2 over r squared. I always put r squared because I'm used to that for force, gravitational force. This versus over r. I guess we're calling this planet 1 and this m2. Don't worry about the negative again. I think it's confusing. It's still important just to know that as those planets get separated, their potential energy increases, just like a ball going further away from Earth. And as they fall towards each other, that potential energy transforms into kinetic energy. And they would accelerate faster and faster and faster, which, of course, there's a net force on them, right? One pulling force from the other planet pulling you forward. There's nothing out there. There's no friction or anything like that. So it's certainly a net force, so it's going to accelerate. If it's accelerating, it's going to gain speed. It's going to gain speed. It's going to gain kinetic energy. Where is it going to come from? It's coming from the potential energy in the system decreasing as they fall towards each other. That turns into kinetic energy. Know that the mechanical energy of the system actually remains constant as they fall towards each other, because again, it's just a pure conversion of energy from transformation from potential energy to kinetic energy. There's nothing to lose energy to out there. There's nothing out in outer space, all vacuum. I mean, if they asked you to graph that, I doubt it. It's a weird idea. It actually would go like this. This approaches zero. So, at a distance of infinity, the potential energy actually becomes zero, which I know seems weird because you'd say, wait a minute, you said it's further and further apart, then it's more and more potential energy. Then how could it be the zero potential energy if they get to infinity? Well, at infinity, the force that they both can exert on each other is zero, because this vector gets smaller and smaller and smaller as they get further and further apart. At infinity, it's zero force. So how can they fall towards each other if you let go of them at that point, if there's no force pulling back towards each other? Therefore, oops, yeah, that makes sense. So there's no potential energy at infinity, I know. And these are all negative. These are all negative values. So all potential energies are actually negative. And if you get further and further away, your potential energy value gets closer and closer to zero. Like -1 joule is greater than -10 joules. When you're close to the planet, let's say -10 joules, and then you go far, far away, and now your potential energy is -1 joule, and you have to scratch your head and think about that and think, okay, so -1 joule is more than -10. Yeah, it's close. It is technically on a number line, right? Don't worry so much about the graph. But the concepts I originally described are more important. How energy transforms and they feel the same force. Okay, moving on. I will make a couple other comments here. If they decided to do this, more than likely, this problem, one would be a light planet, one would be a heavy planet. This takes us kind of back to like the kids pushing on the skateboards and the momentum unit, pushing off each other. Just remember that if he's light and he moves this distance in 2 seconds, this guy ain't going to move that distance in 2 seconds. He'll only move a smaller distance because he's a heavier planet, right? So this would be a smaller distance that he moves, and he'd move a larger distance. Again, assuming that there's two planets flying towards each other. If you started off just holding them at rest and then release them, the lighter one will move the greatest distance, right? And since work is force times distance, and we know the force is the same, the distance is not. He has a greater distance that he moves in any interval of time. Then the amount of kinetic energy he has is greatest, because the work done by the gravity force is the greatest, where the delta K for the small is the smallest for the heaviest guy. Who has the greatest acceleration? The guy on the right. Who has the least acceleration? The guy on the left. It's Newton's second law. A is inversely proportional to m. And know that their momentum actually would be the same, because that ends up being, well, conservation of momentum, technically, right? If they started at rest with no momentum, that at any time later after you've released them and they're flying towards each other, the total momentum has to be zero. And the only way that could be is if the momentum of the planet moving to the left is equal to the planet momentum of the planet moving to the right. It's the only way that works, right? You could also, argue that the impulse, is F delta t. And since they feel the same force, that's Newton's third law, the gravity force, and in any amount of time, delta t, F delta t as a product is the same for both of them. And the impulse momentum theorem says, therefore, that their change in momentum should be equal but opposite in direction. This is actually minus here. All right, moving on. This one quick. Remember, there's your sun. This is your star, boop, boop, or your star actually would go first, and then your planet or your asteroid or your comet or whatever it is. You need to know that the maximum potential energy is out here. The kinetic energy is minimum over here. When it zips around, it's going to flies around the edge. It's a slingshot effect. This is a maximum kinetic energy at this point and a minimum potential, not zero, because it's still got some distance. We just talked about that potential energy is GMM over R squared. That's that R, I always say R squared, sorry, over R. And that R is not zero. So it has a maximum speed here and has a minimum speed out here. The total energy is constant as it goes around and round, as this asteroid goes round and round. Good there. Moving on, I'm nearing the end of my notes somewhat. If we're talking now about something like this, sun's in the center, and you have your planet going like this. This is the planet moving at a some sideways speed. They said represent the kinetic energy of that object, of that planet. That's a little tricky. I mean, you'd have to remember that the orbital velocity is the square root of g times the mass of the sun in this case, or whatever the gravity object is in the middle, over r. So we know if they said, what's the kinetic energy of the planet? We'd actually have to stick that v in there. 1/2 m. Notice it's a square root expression getting squared. So we're just going to undo that. G times mass of the sun over r. What does that end up looking like? It ends up looking like this first m, sorry, this little m right here is the mass of the planet. Because we're talking about the kinetic energy of the planet. So what does that end up looking like? Mass of the planet, g times, or usually write g first, I guess. G times mass of the planet times the mass of the sun all over 2r. That represents the kinetic energy of the planet. This is in a case if it's almost a circular path, which is a constant speed all around. If it's the elliptical path that I was just showing you, you wouldn't use that because the speed changes. Kinetic energy changes, depends on where on its ellipse it is. But in the circular motion, where they show, oh, this is almost a perfectly circular orbit, what's the kinetic energy of the planet? That's how you do that. Moving on. If they asked you about the escape speed, so again, that means if you have a planet and you have a rocket that you want to take off and eventually you're going to shut off your engines because you can run out of fuel. And if it drifts, you want it to literally drift away forever. You don't want it to eventually stop due to the gravity force of the Earth and have Earth pull it back, because that means you didn't escape. You might have left for a while, but it brought you back, like it brings basketballs back if you throw them up in the air. That concept is called the escape velocity. And to do that, what we imagine is to actually escape means that you'll drift further and further and further away from the planet. If you are able to have your rocket achieve some particular speed during the burn, which we call the escape speed, that's the maximum speed it needs to hit. Then if it hits that speed, if it goes into outer space and shuts its engines off, it'll continue coasting at that speed for a long, well, not really, it seemed that way, but slowly, little by little, Earth's gravity is doing negative work because it's pulling it backwards and you're moving forwards. So it would slowly slow you down. But even though you would little by little slow down, you'd only actually finally lose all of your speed all the way out in infinity. And technically, in theory, if you could get to infinity with your rocket, you would actually stop at that moment. At that moment, you'd say, wait a minute, there's no potential energy out here because the force from the Earth is zero now. I'm so far away. I'm infinitely far away. There's no potential energy because I don't have the potential to fall anymore. I don't even recognize any force from the Earth. No potential energy. I've stopped. There's no kinetic energy. That means I've got no energy at all. And therefore, your initial energy, the rocket has some initial potential energy, which would be g times the mass of the Earth, if we were talking about the mass of the Earth, let's say, times the mass of the rocket over r. That's r, right? It's on the surface of the Earth. It has some potential energy. We just don't use mgh. That's for things up, that are moving on the surface in small, delta H distances on the surface. Once we start talking about planetary stuff, that's the potential energy formula. And if it's going to be, reaching some burn speed, and it's going to have some initial, it's not right away. It's, after burning for 10 minutes, maybe for the rockets, it has to reach some kinetic energy. Then all of that energy has to eventually, at the beginning, equals 0 at the end. This is E final all the way out at infinity. So why are we doing this? Because I'm just trying to show you that that's how you get the escape. Oops. That's how you get the escape velocity. Mass of the planet times the mass of the rocket over r. Mass, this is the mass of the planet over here. That cancels. And if you were to solve that for the escape speed, this is now representing BE, the escape speed. Multiply both sides by 2. I made a mistake. I'm sorry. This isn't the mass of the planet over here. This is the thing that's moving. This is the mass of the rocket. Crossed out the wrong one. This is the mass of the planet. Mass of the rocket. So mass of the rocket cancels away. Mass of the planet does not. Over r. And then you would have to square root it. This is called escape velocity. It could be used for any object, any planet. MP represents the mass of a planet or the mass of a sun. And r represents the surface radius, assuming you're shooting it off from the radius of, this is the radius of the planet. You're shooting your rocket off from the surface, I would assume. Maybe not. You could technically launch from outer space, and then r would be the distance from the center of the planet out to wherever you're launching from. But most of the time, we're launching our rockets from surface. So that r represents your initial position when you attempt your escape from that planet. It's usually referenced as a square root in their problems. I don't know why. Either one. All right, that's done. Now we're going to end with our rotational kinetic energy. If something is rotating, we know that that has rotational kinetic energy equal to not 1/2 m, 1/2 I, not v omega squared, because that's the connection between those things, right? I is rotational inertia, omega is rotational speed. If something's rolling down, like a ball, like we did quite a bit of that, then the initial potential energy at the top here converts to not just kinetic energy, not just translational kinetic energy, but rotational energy as well, right? Because as it is moving, it's not only moving straight with translational kinetic energy, it's also rolling. It's actually still rotating as it goes down. So it's a rolling scenario, right? So at the very bottom of it, you'd say the initial potential energy at the top of the ramp is equal to the kinetic energy translational at the bottom plus the rotational at the bottom, right? Knowing that it's always going to be less speed at the bottom than something like a block that just slides down the same ramp with no friction. And that's the reason, because for the block, it gets to take all of its original potential energy and turn it into translational energy, which is why it will get to the bottom first, of greater speed. While the rolling ball actually takes that original potential energy and converts it into two forms of energy, translational and rotational, leaving less available for the thing that actually makes you win the race, which is the translational energy, which means the final speed v at the bottom for the rolling ball will always be less than the final speed v of a block that slid down. Talking about this, we might as well just quickly mention that when we're doing the sphere versus hoop versus disk, this is the disk here. This is the hoop. This is the disk. This is the sphere. The sphere is always the winner, right? And the hoop is always the loser. And the disk is in the middle. First, second, third place. Why? Because the hoop, who always comes in last, has the greatest rotational inertia because all of this mass is out on the edge. The disk and the sphere have mass that's distributed throughout their whole shape. And so that brings some of its mass closer to the center and makes it easier to rotate. Right, moving on. Know that if something's rotating like this, like a platform, then it's the same idea. Kinetic energy is 1/2 I omega squared. You'd have to know the rotational inertia of a disk. I think it's 1/2 mr squared. I don't memorize all those things. I think that's what it is. They would give it to you. Again, you don't have to memorize those rotational inertia formulas. They'll give it to you. Just know that if they talk about something that's here and that thing then moves out to the edge, well, that's a conservation of angular momentum thing. Um, and the angular momentum can't change. This is the skater that's spinning, right? Since angular momentum, like linear momentum's mv, our m becomes I, our v becomes omega. This is representing the initial rotational velocity when the person was here. And omega f represents the final rotational momentum of this platform once the person arrives here, right? And so we know that since the I is going to increase, this is going to be a larger I here than, because things are moving out further, right? That means I is going to increase. Then what does omega need to do? Omega needs to decrease so that the product of those two values still comes out as I initial times omega initial. So yes, its rotational speed is going to slow, but a lot of people would therefore say, oh, therefore its kinetic energy is going to slow. But that's not right. It's a conservation of energy thing, right? Um, so if there's no loss of energy and internal things are just being moved around, the kinetic energy 1/2 I omega squared is actually the same at this position, at this position. Even once it's slowing at the edge, when that reaches the edge, or the solar panels that open up their arms as they're spinning in outer space from these satellites, they slow rotationally as they open up their arms. Does that make them lose kinetic energy? No. They'll be rotating more slowly. Omega will be less, but I is going to be greater because they've stuck their arms out, or the solar panel arms further out. And that happens that go in a way where it just perfectly compensates, and total kinetic energy doesn't change. And you say that has to be, especially for the satellite that's in outer space. That's like a skater, when it opens up its arms at the end of their skaters at the end of their race, they slow, or at the end of their performance, they slow down. Well, this solar panel does the same thing. And you'd say again, if it was losing kinetic energy, what would it be? In what form? And to who? There's no air out there. And you realize, yeah, I guess it's true. It has to be contained, right? Yeah, it is contained. There's nothing for it to interact with. So be aware of that. We're talking about falling objects. They have a ball and they drop it. Then you need to know that as it falls, it's going to be potentially rotating. We start with μg at the top, same idea, but that converts now to translational plus rotational. Same concept that we just talked about with going down a ramp. It doesn't matter whether you're going down a ramp or falling straight down. Same idea. Know that these can be re-expressed if they had to be, right? 1/2 I omega squared. If this was, I don't know, the end, when they say boom, it hits the ground, then this would be omega final. This one will be your 1/2 m v final squared, and that would represent the v that it has as it boom hits the ground. Omega final is representing its final rotational speed boom, at impact. And those two additions, some things summed up, would be equal to that. That's conservation of energy. Right? Almost there. Know this, which is very rare that they talk about this, but technically you can still do work when you're turning something. So if you're applying a force at some angle to something and it's rotated through some angle, then the work done on this as you rotate it, because it's going to gain some rotational speed and therefore some energy, through what mechanism? Through the work that you've done. So it's when we say force times distance for the linear case, it's torque times delta theta. Remember, d is like a theta in rotation and F is like a torque. Delta theta is just the change in the angle. So the work that's done is the torque times the angle that you've pushed it through rotationally. And that would be now in the form of rotational kinetic energy. It's like, work energy theorem for translational, just written for torque. That's almost never mentioned, to be honest with you. And now we're truly at the end, where we quickly talk about power. Power is energy over time. It's joules per second. Joules over seconds. Joules over, I'm sorry, over seconds, which we call that watts. Right. So just remember, if something is giving energy to something else at a rate of 5 joules per second, we call that 5 watts. Or if something is giving something at a rate of 10 joules per second, we call that 10 watts. The rate at which energy is transferred, or the rate at which work is done. How is it usually written in a textbook? Power equals delta, this is work, over delta T, or change in energy over delta T. Remembering that energy and work are both energy units, units of energy. So it's, again, very rarely mentioned. You might get one small question, multiple choice question. My guess, as I've gone through all the problems, they don't mention, for some reason, power very much, but you need to be aware of it. It's how quickly energy. So if they told you that, you had to work out that as it moved from here to here, or as it moved from here straight up into the air, the potential energy, increased by some amount, then it would be that potential energy increase times how long it took. And that would be the power of the thing that lifted it. However much energy it gave to it from point to point, going straight up, divided by the time that it took. Most importantly, notice that the power is inversely proportional to the time. So if you can transfer that same amount of energy, mgh, in a tiny amount of time, because the motor that you're using is super strong, puts out a lot of force, and it's a powerful motor because the amount of time, delta T, will be tiny. Boom, there, it's already up. That means delta T being tiny, power is going to be large, right? Lastly, I will point out that there's another formula. This is on your equation sheet, F times V. If they say, usually they say some crane or something is lifting this at a constant speed um, by a crane, what is the power of the crane? If it's going at a constant speed, well, that means the lifting force from the crane, which is the tension, is equal to mg if it's constant speed, not accelerating. And then that means that force, Ft, would just be mg because it's lifting it at a constant speed. If they give you that constant speed, you would just plug in that constant speed and or mg, or recognize that's proportional. The power is proportional to V. So if you have a machine that can, move you upwards at a constant speed twice as fast as another machine, well, twice as fast as the V, and it's twice as powerful. It's got twice the wattage. Is there any other comment? I guess there's one final comment. If you're looking at not a position versus distance graph, but a position, I mean to say, not an energy versus distance graph, but an energy versus time graph, who knows what the shape is? It can be this, it could be a curve, it can be anything, right? I'm just going to do the linear just to point out just the idea that the slope of this graph is power in both cases. It's the power of the thing that you're actually using to move the object. It's the power of the thing that's actually causing this kinetic energy of the object to increase. It might be a machine that's causing the car's kinetic energy to increase. So that's the power of the engine, right? Or it's a pulley lifting something, right? And the potential energy of the piano is going up. But what's lifting it? The crane. So this represents the power of the crane, right? And how do I know that? Because any energy is in joules and any time is in seconds. Rise over run, well, that's joules over seconds, right? That's watt. That's power. We end there. I'm done with energy. We talked about energy. Um, any more? So I still have momentum. So I think tomorrow, which is Monday while I'm in school, I'm going to do a momentum one. And then we'll be done. Um, I don't think I'm going to review all the I'd make videos for all of the rotational stuff again and all of the simple harmonic motion. You could always go back and watch those videos if you want. I mean, I post everything online for you to watch. So I think the most important part was to review all of the old stuff prior to rotation and simple harmonic motion, I think. Um, so technically there's one more video coming for momentum. All right, everybody, that ends our time together. I hope you found that useful, and I will get to say one last time. Do you know what I'm going to say? One last time, I get to say, see you soon.